So we ended doing these practice problems and identifying the types of intermolecular forces present, and then deciding who would have the greater intermolecular forces based on the types. So we finished with this. So we're going to keep doing some more practice. Now, if you notice on this graph, this is oxygen, right? It's in group family 6, and then below it is sulfur, and then below that is selenium, and then below that is tellurium. And you notice that this is showing boiling points, all right? And you should see that water has the highest boiling point of anybody else in group 6 because it's capable of hydrogen bonding. And then notice that it drops back down, okay? And then after sulfur, the boiling point continues to rise. And the reason that is because these get heavier and heavier and heavier, so the dispersion forces get stronger and stronger and stronger, okay? And then the same thing happens with group 5, family number 5, which is the nitrogen family. So you've got nitrogen attached to hydrogens. Now, this guy's capable of hydrogen bonding. So because of that, it has the highest boiling point of any other element in group 5. So then phosphorus is below nitrogen, and then arsenic is below phosphorus, and then antimony is below arsenic. So it drops back down, but then steadily increases as the molecules get heavier and heavier and heavier because the dispersion forces start to increase. Okay, so that's just what this graph is showing with the different boiling points and how drastically different things are with hydrogen bonds, as opposed to all of these guys are bent, so they're polar, and then all of these guys are trigonal pyramidal, so they're polar, but the hydrogen bonding plays a huge significant role in boiling point relative to just dipole-dipole. Okay, and then look at these guys only have dispersion forces, right? Carbon, and below carbon is silicone, and then germanium, and then tin, and they aren't capable of hydrogen bonding, but the heavier and heavier they get, the more polarizable they are, and therefore their boiling points increase. So I would like you to look at these guys, and you can draw them if you have to, and I would like you to determine the intermolecular forces present for each atom or molecule, depending on what it is, and then answer the questions. Which is likely to have the largest intermolecular dispersion forces, also known as London dispersion forces, and which of them is going to have the greater dipole-dipole attractive forces? So I'm going to give you a brief moment to answer those questions. So I've gone ahead and drawn them all. Okay. Every molecule or atom has dispersion forces. So they asked you in the first question to pick one which would have the largest dispersion forces. Well, the greater the dispersion force, or greater dispersion forces, are determined by heavier molecules because they're more polarizable because they have more electrons. So that's going to be Br2. It's the heaviest of all of these substances. So because of that, it will have the strongest dispersion forces. Questions on that? Okay. Now, which is most likely to have the largest dipole-dipole? Well, which substances have dipole-dipole, meaning they're polar? Well, not Br2. This is nonpolar, so it only has dispersion forces. This is just an atom, so it only has dispersion forces. Nitrogen gas, it only has dispersion forces. It's nonpolar. So HCl and HBr are our two molecules that also have dipole because they're polar, right? They have a more electronegative element pulling the electrons closer to itself and nothing to cancel out that dipole. So how do you decide who has the larger dipole? Well, the greater the difference in electronegativity determines a stronger polarity or a greater polarity. Well, HCl is more electronegative than bromine, so HCl has a greater pull on the electrons, making this dipole stronger. So HCl should be this answer down here. Any questions before we're going to do some more practice? Okay. So this says identify all forces present and list the substances in order of increasing boiling point. So what does that mean? That means low boiling point to high boiling point. Now remember, to get something to boil, you have to completely break intermolecular forces. So things that have high boiling points, it means they're hard to boil. They have strong forces holding it together. Things that have low boiling points have weak forces holding it together, meaning they're so weak that they'll happily boil, or they'll easily boil. And then remember, boiling means a liquid turning into, oh, what is happening? A liquid turning into a gas. So I'll give you a second. All right. So I drew them for you. Hydrogen gas is nonpolar. It only has dispersion forces, and it's the lightest, so it's the least polarizable, so it will boil the easiest. Now let's think about it. What state of matter under standard conditions, like your room right now, is hydrogen? Would hydrogen be? Well, it would be a gas, right? Things that are already gases obviously have very weak dispersion forces holding them together. They've already boiled if they're already in the gas phase, okay? And then you have neon, which only has dispersion forces, and we know neon is a gas, right? But it's a little bit heavier than hydrogen, so that's why it has a little bit higher boiling point. Now, if it's a gas under room conditions, that means at 25 Celsius, right, it has already boiled. We've already passed its boiling point, okay? Carbon monoxide has dispersion forces, but also has dipole-dipole because that oxygen yanks harder on the electrons. So it has a little bit higher boiling point. Now, carbon monoxide is a gas, okay? It is a gas. So it has already boiled also, but because that's dipole-dipole, that's having dipole-dipole is a little bit stronger than just having dispersion forces, all right? And then HF, pretty darn close to room temperature, but it's a liquid, okay? And it has hydrogen bonding. This hydrogen can hydrogen bond because it's attached to a fluorine. And hydrogen bonding is a stronger force than just a dipole-dipole. And in fact, it's so strong that HF actually still remains as a liquid. It doesn't, in fact, boil off and turn into a gas at room conditions. That's because hydrogen bonds in general are stronger than a dipole-dipole. Okay, now barium chloride does not have intermolecular forces. This thing is ionic. It's a salt. Guess what state of matter barium chloride is? What state of matter are most of our salts? Solids, right? So barium chloride, ionic forces are way stronger than any sort of intermolecular force, like a lot stronger. So they're so strong that these substances will stick really, really close to one another. They're super attracted to one another because they're of the cations and anions, and they'll remain as a solid under most room conditions. Okay? So I actually looked them up for you. These are their actual boiling points. So this is when hydrogen boils, and then neon, and then carbon monoxide, and then HF, and then barium chloride. Look how high this boiling point is. Think about it. Have you ever heard of a salt turning into a gas? Right? Maybe you can melt it, yeah, but trying to get it to a gas, this is a huge boiling point. All right? Ionic forces are super duper 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 strong. All right, so let's try again. So identify the intermolecular attractions present and then pick the highest boiling point. So I'll give you a second to do that, please. All right, so we have these three molecules. These are obviously organic molecules, right? They're carbons and hydrogens and carbons and hydrogens and oxygens. If you did not know, but you will know now, hydrocarbons, meaning they just have carbons and hydrogens, are nonpolar. They're all the dipoles cancel out. They're all nonpolar, so they only have dispersion forces. Okay. This is methanol and this is ethanol. And both obviously have dispersion forces, but they also are both capable of hydrogen bonding. So if they both have the same types of forces, they both have dispersion forces, they both have hydrogen bonding, how do you choose who has the highest boiling point? Any suggestions? Highest boiling point means hardest to boil. Hardest to boil are stronger intermolecular forces. Yes, the heavier one. Why? Because this guy has stronger dispersion forces because it is more polarizable, because it is heavier. It has more electrons, better chance at an instantaneous dipole. So it's going to be ethanol has the highest boiling point because it has the strongest forces holding ethanol molecules together to other ethanol molecules. Alcohols are polar because of this bent end right here. So polar, polar. That bent right here will not allow these dipoles to cancel out. Okay. So then I looked them up for you. So right, standard room conditions is 25 Celsius. Okay. So this is ethane, and its boiling point is negative 89, meaning it has, in our room, if we had ethane in there, it would have already boiled and it would be a gas because it has the weakest intermolecular forces. It can just easily escape into the gas phase. Whereas methanol is a liquid, right? It doesn't boil until 64.7, which under room conditions, it would be a liquid then. And then ethanol doesn't boil till 78.37, so it's a liquid also under room conditions. But again, ethanol has a slightly higher boiling point because it's heavier and more polarizable. Questions? Okay. Go ahead and draw these and answer the question, please. So someone last class asked me, what is the difference between CH3 and C2H6? And the answer is nothing. There is no difference. They're just two different ways to write the same compound. Wow. So you should notice that both of these are hydrocarbons. They're carbons and just hydrogens, okay? Which means they experience dispersion forces only. Now notice, look at, a lot of times you'll notice in organic compounds, they try to write them in order. So like this is like a compacted version as opposed to like CH3, CH2, CH3. But again, they mean the same thing. This is ethane, this is propane. Okay, and so if both of these only have dispersion forces, the heavier one is going to have the stronger dispersion forces. It is more polarizable, better chance at instantaneous dipoles, which means it has a higher boiling point. So molecules of propane are harder to boil than molecules of ethane. So if you look, this is a lower number boiling point than this. Now you should notice if our room temperature is 25 Celsius, these have already boiled, meaning they've already escaped into a gas phase. So their forces are relatively weak altogether, but propanes are stronger. It's a little harder to get propane to boil. This is a higher temperature. Okay. So go ahead and try this one. Now this one is asking about melting point. Melting point is turning something from a solid into a liquid. Okay. Now what are we doing when we're melting? We are weakening intermolecular forces. We're not breaking. We're just weaken the intermolecular forces. But again, the stronger the intermolecular forces, the harder something is to melt. So I'll give you a second to kind of draw them and look. So yes, polarizability depends on how heavy or molar mass because it is directly correlated to having more electrons. Remember, it's a distorted electron cloud that creates that instantaneous dipole. So the more electrons something has, which is directly related to the heavier something is, the stronger the dispersion forces can be. So I drew them for you. And I also thought it would be good to note, right? This is propane. What state of matter do we know propane to be? Propane tanks. What are they?
Gas.
Gas. Thanks, Andy. Now, this is ethanol. Okay. Ethanol is drinking alcohol. What state of matter do we know drinking alcohol to be? Liquid. Great. Liquid. So look, why is ethanol a liquid while propane is a gas? Well, propane has dispersion forces only. That's pretty weak, so it'll readily escape into the gas phase. Whereas ethanol is capable of hydrogen bonding. So ethanol molecules and other ethanol molecules will readily want to interact with one another, meaning they don't easily just jump into the gas phase because they're busy being attracted to themselves. So ethanol, under normal room conditions, remains a liquid because of stronger intermolecular forces. Questions? Yeah, you can turn things into solids. You can also do that right by messing with pressure. So we're going to talk a little bit about that later. So here are their numbers. This is the melting point of ethanol. So it is melted, okay? And this is the melting point of propane. So this guy is melted, but it is not boiled. This guy, propane, we know is melted. It's already been turned into liquid and it's boiled at 25 Celsius. Okay, so which of them has a higher melting point and why? So go ahead and try to answer. Okay, so we've got methanol, which has dispersion forces and it also is capable of hydrogen bonding. And now you don't need to know this guy's name. However, when you used to have to do this. So when you number the carbons, they call this 1, 2, propa, because there's 3 carbons, di means 2 alcohols. So 1, 2 propadiol is how they would name it. Again, you don't have to know how to name it. I'm just kind of telling you. So then these both have dispersion forces. These both are capable of hydrogen bonding. But this guy, the propadiol, should have a higher melting point. It should be harder to melt for 2 reasons. One, it's capable of hydrogen bonding in more than one location. Also, it's bigger, it's more polarizable, it has more electrons, it's heavier, therefore it has a better chance of having stronger, or it will have stronger dispersion forces. All right. So then there's their numbers. This is the temperature at which methanol melts, and this is the temperature at which the propadiol melts. This is a higher number than this number. It's a higher melting point. So identify, or which species has the higher boiling point. So again, and identify the intermolecular force acting on each. So I'll give you a second. All right. So ionic bonds will overpower any intermolecular force. True bonds are way stronger than intermolecular forces. So sodium chloride absolutely is going to have a higher boiling point. Think about it. Sodium chloride is a salt. It's a solid under room conditions. Water is a liquid. Okay, water already has weaker intermolecular forces. Why? Because it can't even stay a solid under room conditions. Things that are solid have really, really strong intermolecular forces, right? Because things are really attracted to one another. Okay? Questions? So look at this is the temperature at which salt boils, right? To try to get a solid salt, sodium chloride, to turn into a gas takes huge amounts of energy. All right. Okay, so this concept of vapor pressure we've gone over before, but we need to go over it again because intermolecular forces will also determine vapor pressure because vapor pressure is directly linked to boiling. Does anybody remember what the definition of boiling is? Actually, let me take that back. Let's go first. Does temperature determine if whether something boils? No, correct. No. Now, can you mess with temperature to force something to boil? Yes, sure. But what does boiling point? What is the definition of boiling point? Boiling point is when vapor pressure equals atmospheric pressure. That's the definition of boiling point. So there is a way that we can cause an increase of vapor pressure by heating, okay? But boiling point is not determined necessarily by temperature, meaning you can mess with pressure and force things to boil. That's really the true determinant. So I'm going to draw a container. And hopefully you draw this with me too because I think it will be helpful. And we're going to use water. Water is the easiest, most common substance we know and we work with, okay? And I'll do water and we'll do it at 25 Celsius. Okay. Now remember that the temperature is the measure of the average kinetic energy of the molecules, meaning some molecules are moving a little bit slower and some molecules are moving a little bit faster. And in fact, some molecules are moving fast enough to escape into the gas phase even though the water is not boiling. Okay? Some of them will escape into the gas phase. They'll be able to. So this right here, these gas molecules have vapor pressure. They have pressure because they're in the gas phase. Now let's say we heat up the water. Okay, and we've heated it to like 85 degrees Celsius. Okay, well, if you heat it to 85 degrees Celsius, on average, the water molecules should be moving faster, right? That's the measure of the average kinetic energy. They should be moving a little bit faster. Okay, so what does that mean in terms of the number of gas molecules on the surface of the water? More or less? More. Good. So if you heat them up, on average, you will have more of these molecules that have been able to escape into the gas phase. Now, water's not boiling yet, right? Because we know water doesn't boil till 100. However, if you supply more energy, more of the molecules will be able to escape into the gas phase. So that means we have more vapor pressure, right? And if you heat them up until the vapor pressure equals atmospheric pressure, aka 1 atmosphere or 760 torr, you will be boiling. And for water, that happens at 100 degrees Celsius, meaning the vapor pressure would be 1 atmosphere at 100 degrees Celsius. That meets and exceeds atmospheric pressure. So you want to think of these like liquid molecules trying to jump out into the gas phase. Well, what's holding them down? Well, the atmosphere is pushing down on them. That's what keeps them in the liquid phase. So the more the molecules can push against the atmosphere, the more that can escape into the gas phase. Now, we can do this by heating, that's the most common way, or we can do it by removing pressure. That is a much more difficult way to get them to boil. Okay? So you go, well, what kind of things will readily escape into the gas phase? Well, things with different vapor pressures. Okay, so if you have um, a weak intermolecular forces, it means those molecules really don't want to be with other molecules of themselves. So they will readily escape into the gas phase easily. And gases exert high vapor pressures. So what does that mean? That means they boil easily. So low boiling points. So what does that mean in terms of strong intermolecular forces? So things that have strong intermolecular forces, like let's say solids and even liquids, right? They have super low vapor pressures. They do not escape into the gas phase very easily. And because of that, they have high boiling points. They are hard to get to boil. So now we've tied in boiling point and vapor pressure with intermolecular forces. Okay? So things that are termed volatile means they escape. They're specifically liquids that escape into the gas phase easily. They evaporate easily. Can you think of like a common household substance that you've probably used in your life that is considered volatile and escapes into the gas phase pretty easily? What about rubbing alcohol? Rubbing alcohol, it's also called isopropyl alcohol, right? Now, why rubbing alcohol? Well, if you've ever noticed if you put rubbing alcohol on like your skin, it feels cold. And the reason it feels cold is because it's quickly evaporating off of your skin, which is why your skin tends to feel cold. So that's an example of a volatile substance. And then don't forget that the heavier substances are, the more dispersion forces they have, so they won't escape as easily into the gas phase. So again, we can change vapor pressure by changing temperature, because by changing temperature, we change the average kinetic energy. And the more kinetic energy these molecules have, the better of a chance they have of meeting and exceeding the atmospheric pressure that's keeping them in liquid or solid. And back in the day, you used to have to calculate vapor pressure, but we don't do that anymore. So again, this is that Boltzmann distribution curve, right? It's just a curve, and where we focus on the area under the curve. And what this is saying is, this is like, for example, where something will boil, okay? So 1 atmosphere. It's called a normal boiling point, okay, when you meet and exceed 1 atmosphere. So if the molecules are at lower temperature, you have less, the area under the curve is what matters. You have less molecules escaping into the gas phase, whereas if you heat them up and they have more energy, you have more area under the curve, therefore more molecules are able to meet and exceed this amount of energy. I guess I shouldn't say 1 atmosphere. This is minimum kinetic energy, whatever this is, okay? Now, this is what I was trying to do, and I mixed up the slides. So again, this directly correlates to boiling point. So we're going to focus on diethyl ether, ethanol, and water. Now, I'll draw diethyl ether for you, but will you please draw ethanol and water really quickly? Draw ethanol and water. Okay, so this is diethyl. Ethyl is a 2-carbon chain, and there's 2 of them. 2-carbon chain, 2-carbon chain. That's why they call it diethyl. And then ethers have an oxygen thrown in the middle of the carbon chain. This thing is nonpolar, which means it only has dispersion forces. Whereas ethanol is polar, and it also is capable of hydrogen bonding. And water is also polar, and it's also capable of hydrogen bonding twice. And it's small. Okay. So if you look at that relative on the chart, look at, so normal boiling point just means the boiling point at 1 atmosphere, or 760 torr, right? 1 atmosphere and 760 torr are the same thing. That's all the word normal means, right? Because that's like a normal setting or a normal room. So look at how easily diethyl ether boils, because it only has dispersion forces keeping it in the liquid phase. And then you can look at ethanol. It takes a little bit more energy. You got to heat it up hotter to get it to boil, because it has hydrogen bonding. So ethanol molecules are attracted to other ethanol molecules, keeping it in a liquid state easier and harder to boil. And then water is capable of hydrogen bonding twice. It's smaller, so the water molecules can get closer to one another, experiencing a greater force of attraction. So water is even harder to boil than ethanol. Okay. So notice that the vapor pressure equaling the atmospheric pressure, right, because this says vapor pressure, is the boiling point. When the vapor pressure of the substance equals the atmospheric pressure, you are at that substance's boiling point. Okay. Please draw these 2 molecules and identify all forces that are present. So I'll give you a brief moment. Okay, so this is what I have. Okay, now based on the drawings alone, so you know which forces are used based on whether something is polar or nonpolar. If something is not polar, it can only have dispersion forces. Something that is polar has dipole-dipole forces because it's polar, because it has an overall net dipole. So based on just looking at these structures, we know that dipole-dipole tends to be a stronger force than only dispersion forces. However, I'm going to present you with the next slide. So when you read this problem, it says, based on the information in the table, which of the liquids has a lower vapor pressure and why? So let's talk about what a low vapor pressure means. Low vapor pressure means it doesn't escape into the gas phase readily. And things that don't escape into the gas readily tend to have higher boiling points, right? Which is what is in this graph. They're harder to boil. So obviously, based on boiling points, it's this guy has the lower vapor pressure. It's harder to get it to boil, so therefore it doesn't escape into the gas phase very easily. So the answer is B, which then kind of contradicts what we said, though, because we said this guy is polar and that it has dipole-dipole. And in general, because it's polar and it has dipole-dipole, well, because it's polar, it is dipole-dipole. That's what it means to be polar. So because as dipole-dipole, we generally tend to think that dipole-dipole is a stronger intermolecular force than just dispersion forces. And this guy only has dispersion forces because it's not polar, so it can't have any other forces. So what do you think happened here? Why is this guy harder to actually boil than this guy? Who got replaced and what did it get replaced with? This guy had 4 bromines around it. Now, one of the bromines, whose molar mass is what? 79? 80 grams per mole? One of them is removed and replaced with a hydrogen, and hydrogen's molar mass is 1 gram per mole. So you've basically taken a heavy atom that was originally attached and replaced it with a lighter atom. So it's very apparent that by doing that, the dispersion forces in this guy are much greater than when you didn't have all 4 of them as bromines. And so obviously the dispersion forces are stronger than any dipole-dipole forces in here. So the dispersion forces basically overpowered the fact that CHBr3 has dipole-dipole. Okay. Any questions? Atmospheric pressure is caused by I guess the atmosphere pushing down on the surface of whatever system you're looking at. So gravity, yeah. Okay. So look, this means ionic. Ionic bonds and covalent bonds are stronger than any intermolecular force. So ion dipole is the strongest type of intermolecular force. This is like salt water. Hydrogen bondings are the second strongest, and then dipole. We didn't talk much about ion-induced dipole. I'm not really too worried about it. Dipole-induced dipole, meaning something that's polar, forcing something to be polar that wasn't polar to begin with. And then dispersion forces in general are the weakest of the intermolecular forces. Now, this hierarchy is assuming that we're comparing things of similar size. Otherwise, we start comparing apples to oranges, and you can't say one over the other, okay? This is in general of things that are similar in size or molar mass. So we've discussed how boiling point and melting point and freezing point are determined by intermolecular forces. So now we're going to talk about these other three things: viscosity, surface tension, and capillary action. So here we go. Viscosity is the resistance of a liquid to flow. How viscous something is depends on how easily the molecules of the liquid are able to slide past each other. Okay, so if something is very, very viscous, if it has high viscosity, that means the molecules do not flow past each other easily. So think of like syrups or molasses, okay? So things with high viscosity have slow flow. So look at this. This is considered low viscosity, right? This is the smallest number up here. This would be considered high viscosity relative. This is the biggest number down here. And look at the viscosity or resistance to flow. So this would be like, if you want to consider this thicker, this would be thinner. And obviously, these are hydrocarbons, okay? And they're getting bigger and bigger and bigger and bigger. So this is like more and more and more and more and more dispersion forces. This guy would have the strongest dispersion forces relative to this guy, which would have the weakest. So this guy is the most viscous. It does not flow as easily. Decane does not flow as easily as hexane does, okay? And again, stronger intermolecular forces mean that the molecules will be so attracted to each other that they won't slide past each other. The more molecules can slide past each other, the better they flow. And things that slide past each other easily are things that aren't attracted to themselves. So weak intermolecular forces are low viscosity, and high intermolecular forces are high viscosity. All right. Surface tension. Okay, so on surface tension, water, for example, which is capable of hydrogen bonding, certain substances, or I guess this is a bug, for example, will not break the surface, like just fall right through, because of the attraction of water molecules to itself. So instead of the water molecules just completely breaking the intermolecular forces of hydrogen bonding, they kind of bend with it. And in terms of surface tension, they bend inward, right? And that's what prevents this bug from like falling through the water. Now, every substance has a maximum allowed. Like we can't do this specifically, right? Because we would put too much pressure on this surface for water to be able to handle, but this little guy doesn't, and that's just showing you the intermolecular forces of water just choosing to stick to itself, and so they feel like they kind of like pull downward instead of just break and letting the bug fall through. So again, that happens because the intermolecular forces that keep water together instead of just breaking right apart. Okay? Now, cohesion and adhesion you should have heard of in biology, so we'll talk a little bit about the biology concept of this. So cohesion are molecules that want to be attracted or bind to other molecules that are similar, okay? That's called cohesive. Adhesive are substances or molecules that are sticking or binding to a surface, like a piece of plastic or a piece of glass or a table or whatnot, okay? Now, these two forces are what help capillary action. So does anybody remember in biology where you learned about capillary action? So capillary action is like the spontaneous ability of liquids to rise up a narrow tube Where in biology did you discuss capillary action? Do you remember? Let's see. Photosynthesis? Yes. Specifically, what part? Yes, plant roots, right? You have roots, these are these narrow tubes, where water climbs up the roots to nourish the plant, right? To provide hydration to the plant. So the water sticks to itself, but it also sticks to the root of the plant, which allows the water to climb up the root of the plant and, fertilizers and any other things to, keep the plant healthy and alive. So that's like the biology concept. But in terms of chemistry, for example, let's talk about a test tube. So we know water likes itself, right? Water has hydrogen bonding and it sticks to itself. However, water is strongly adheres to glass. And because of that, because it adheres to the glass, it is that the reason that is so when it sticks to it, it pulls down and it forms our meniscus, which means while water does have cohesive forces, meaning water molecules are attracted to other water molecules, water's cohesive forces are not as strong as water's adhesive forces, specifically to the material of glass. And because of that, you see the water would rather stick to the glass and pull down into a meniscus than to itself. Whereas mercury does not have very strong adhesion to the material of glass. Mercury's cohesive forces are greater than its adhesive forces to specifically glass. So if its cohesive forces are stronger, it would rather stick to itself. So a bunch of mercury molecules sticking to itself rather than to the glass. So it forms like the opposite of a meniscus. It actually is like a little bit of a dome. Okay? Questions on that? Now, think about a penny though. A penny where water, you put a bunch of drops on a water. Now, water doesn't stick to a penny per se super easily. However, water is so cohesive with itself and so attracted to itself that when you start to put it on a penny, it will eventually form a dome on top of the penny before it starts sliding off the edge. And that's because water, has strong intermolecular forces and is really, really attracted to itself. Okay? That's cohesive forces. So this is just a summary of what I just said. Okay? You can read this when you pull up the notes. This is not necessarily specifically on topic, but it is something I want to kind of show you because it's pretty cool. It's what I call super cool. So this is super cooling, right? This is the cooling of a liquid where you take some liquid, and of course we're going to use water. It's the most common one we talk about. And where you get the liquid to get below its freezing point, yet it doesn't freeze. And the reason this generally can happen is because it happens fairly quickly. It's cooled quickly, which means really, really low temperatures, and it's left undisturbed. If molecules aren't moving around, they don't have a chance to interact with one another. So if you don't disturb them, and you can get them to cool down really, really fast before they recognize each other, those intermolecular forces are not seen. They're not recognized. And you can keep a substance, for example, and have it be a liquid even though you're well below its freezing point. So I'll show you this video. I have no idea where they are. They are not here. It's negative 16 degrees Celsius wherever they are, which is so cold.
This is our third run. We're at 16 degrees below centigrade. And we're just going to grab that bottle and see what happens when you try to pour it out, if anything. Anything interesting happen? Look at that. Oh, now it's actually freezing.
So once he disturbed it, all of those molecules recognized each other, and so all the hydrogen bonds instantly started to form, and it solidified like in a moment. You could technically try this at home in a freezer, but you'd have to put something in a freezer that's like in your garage, like one that isn't going to get touched, because The second you like open a refrigerator door and your like other freezer, the second those water molecules move, if they don't cool down fast enough, which they likely wouldn't in a freezer, they're gonna recognize each other, and you'll pull out a solidified container. So super freezing or super cooling is kind of difficult to do. FP stands for freezing point, and BP stands for boiling point. Now, of course, if you can super cool something, you can also superheat it, which is where you take a substance, and again, we're going to use water, but you take a liquid and you heat it past its boiling point, yet it doesn't start boiling. And again, this can happen by not the molecules not being disturbed and heating them up fairly quickly. So they're going to use a microwave. Now, this can only happen with pure water. This can't happen with like I mean, when I say pure, like distilled water, this can't happen with tap water because tap water has impurities in it, and those impurities will instantly always cause the substance to boil because it doesn't allow, like, they will get in the way of the water molecules, and you won't be able to superheat it. So this only really works with pure, like for this example, distilled water. So you can kind of show this. This one is a Mythbusters.
If you overheat water in a microwave, you may take the cup out of the bowl, and then the water is going to explode in your face, injuring you or burning you in some horrific way.
We're going to time how long it takes to bubble. After a little research, Adam and Jamie know that the only way water could explode is if it's being superheated. That is, heated beyond boiling point, without actually boiling. Tap water always boils because it has impurities. Distilled water has no impurities. That means no boiling. We put 2 cups of water in the microwave, 1 distilled, 1 tap. When the tap water boils, they'll know that the distilled water has become superheated. Just dropping in a sugar cube should make the boiling process happen instantly and violently.
Spectacular.
That would suffice.
That was exploding water?
It erupted, it left the container.
Yeah.
Quite a bit of it.
If someone were holding the cup, they would definitely have severe burns. But if straight tap water can't explode, how likely is it that people will be scalded by exploding beverages?
On your average day in your average house, it's not very likely. However, with the hundreds of millions of people using microwaves every day to boil water, reboil water, I'd say it could happen a few times a year around the world. Myth, absolutely true.
All right. So this is one I would like you to not try at home. It could be really, really dangerous. But yeah, these are just different ways of kind of making them happen so quickly that the intermolecular forces that would cause something to freeze or overcome and boil can be not recognized, and then you can get things below their freezing point or above their boiling points. All right, so I want to kind of go over this phase change with you because, right, changing states of matter has everything to do with intermolecular forces. So we're going to talk about all the different ways we can change states of matter and what it means in terms of intermolecular forces. So when you take a solid to a liquid, it's called melting, and I'm pretty sure you know what melting is. So what happens during melting? During melting, we weaken intermolecular forces. However, if you take a liquid and try to freeze it to turn it to a solid, remember that our solids are, by definition of being solid, are things that are really, really close to one another, right? So things that are really close to one another are things that have high attraction to one another. So freezing involves strengthening intermolecular forces. Okay? So vaporization or evaporation is liquid to gas, right? When you turn a liquid to a gas, you completely overcome all intermolecular forces. So to take a gas and turn it back into a liquid, you got to get those gas molecules to come back together close to each other. So this would be a strengthened intermolecular force. Now, sublimation is a solid straight to a gas, kind of like, liquid nitrogen does sublimation. Oh, I'm sorry, my bad. Dry ice does sublimation, okay? It goes from a solid straight to a gas, completely skipping the liquid phase. So from solid to gas and during sublimation, we completely overcome all intermolecular forces holding the solid together. And then a less commonly known term that I'm going to tell you, but you don't really see it very often, I'm still going to tell you about it, is a deposition, where a gas actually turns back into a solid. That would be a complete strengthening of intermolecular forces if you want to take a gas and turn it back into a solid. It's called deposition. Now remember, when we're doing these, we're not changing the identity of the substance. So we're not breaking bonds, we're breaking forces. If you're breaking bonds, you're doing a chemical reaction, not a physical change. Okay? So I would like to take a moment and have you do these practice problems. However, I would like you for a brief moment to skip B and D, and we'll talk about those separately. So please work on A, C, E, F. I'll give you a couple minutes to answer the questions. All right, so I'm going to start back over since I forgot to turn the record on. So highest boiling point is HCl because it has dipole-dipole forces, which are stronger in general than just dispersion forces alone. So it's the hardest to boil, which means HCl molecules will be attracted to other HCl molecules and won't want to be ripped apart and escaped into the gas phase. Lowest vapor pressure, meaning not escaping into the gas phase very easily, which is interesting. If you look at these guys' states of matter, Cl is a gas at 25 Celsius, bromine's a liquid, and iodine's a solid. So obviously the solid does not give off a lot of vapor or gas, okay? Has the lowest vapor pressure because it has the strongest dispersion forces, because it's the heaviest. It is the most polarizable. It has a greater chance with more electrons of an instantaneous dipole. And in fact, its dispersion forces are so strong that it actually exists as a solid. It doesn't have any other forces but dispersion, but those dispersion forces are so strong that it's so attracted to itself that under room conditions, it sits as a solid. Okay? Lowest boiling point. So these are all hydrocarbons. Hydrocarbons only have dispersion forces because they're nonpolar. They're all nonpolar. Okay. The lowest boiling point means the easiest to boil. So methane is the easiest to boil because it has the weakest dispersion forces. It's the lightest. It's the lowest. It's the least polarizable. So it'll boil the easiest. And then the highest boiling point is going to be HF. HCl and HBr are dipole-dipole, but HF is hydrogen bonding. And hydrogen bonding is a stronger force in general than dipole-dipole, making HF have the higher boiling point of the three. Any questions on those before I do freezing point? Because I think freezing point can be a little bit tricky. All right. So highest freezing point. So let's talk about freezing points. I'll do them in terms of negative numbers and then positive numbers. Okay. So a high freezing point means, so this negative 10 is a bigger number than negative 20, right? If we're talking about freezing points. So a high freezing point means something is easy to freeze. So things that are easy to freeze are things that like to be solids, okay? Which solids have the strong intermolecular force. Okay, right? Solids have to be really, really close to one another in order to maintain solidity. So, if they want to be close to each other, it's because they're really, really attracted to each other. So, of these, who has the highest freezing point? Meaning, who turns into a solid the easiest? And that is going to be sodium chloride. It's ionic. Ionic is going to trump any sort of hydrogen bonding forces. And in fact, think about it. Water's a liquid. HF is a liquid under room conditions, and sodium chloride is a solid. It freezes easily. So what I need you to get over is the whole concept of freezing and boiling have to do with temperature. And I know it's easy to think of that because we think of water very commonly, but like salt is technically already frozen in your house. It's frozen. Is it cold? No. But its freezing point is so high that it just freezes super easily because ionic substances are really attracted to themselves. The cations and anions are a super strong force of attraction, making it easily solidified. Okay? So now this is low freezing point, which means low freezing point would be hard to freeze. So things that are hard to freeze are things that don't want to be with themselves. They're like, oh, I am not attracted to myself. I'm going to stay as far away from myself as possible. And therefore, like, right, when you're trying to get things to freeze, if you want to like look at my hands for a second, when you're trying to get things to freeze, you're trying to bring them together. So things that are freezing to solidify want to be attracted to each other. So if they don't want to freeze, they're things that really don't want to be really close to themselves. So for this one, this is dispersion forces only. This is dipole, and then this guy is dispersion forces only because carbon dioxide is nonpolar. But this has the weakest dispersion forces, all right? So it's going to be really, really, really difficult to get nitrogen to freeze. In fact, think of liquid nitrogen. When you take liquid nitrogen, have you ever seen it in person? If you take liquid nitrogen, if I were to take some, and we used to do this as a demo, and I dump it into a glass, what is it doing at room temperature? Does anybody know what it does? It boils. So like nitrogen is so unattracted to itself that even at room temperature, if you try to keep it a liquid, it'll just straight up evaporate into a gas. It doesn't stay. It boils. It boils at such a low temperature, like negative something degrees, that it has super weak intermolecular forces. So it's going to boil off into a gas. So if you can't even keep it a liquid, you're never going to get it to be a solid. I shouldn't say never, but it'd be very, very difficult to get it to be a solid. Okay. Any questions on these? So this is where I'm deciding to stop.